Hi, I'm Jonathan, and this video is about my final year project, the lockpicking robot. As locks are mechanical by nature, they are affected by tolerance issues due to manufacturing processes. This leaves them susceptible to lockpicking techniques such as single pin picking or SPP. It is a fact that any pin tumbler lock can be defeated by SPP. Some high-end locks may take an inordinate amount of time to be defeated in such a way, but the statement still stands. Any pin tumbler lock is susceptible to SPP attack. SPP works by applying a rotational force to the core of the lock, commonly referred to as tension, and then raising any binding pins to the shear line as they appear. Tension is applied by a tool known as a tension wrench. These are usually referred to as top of the keyway or bottom of the keyway, depending on what part of the lock they interface with. A pick is used to manipulate the pins and bring them to the shear line. When a binding pin is raised to the shear line, the rotational displacement caused by the tension prevents the pin from falling back down. This is what allows the lock to be picked without having to push all the pins up to the shear line simultaneously. This project was proposed with three main objectives. The first was to create lock analogues to mimic the function of a commercial lock in a larger scale. The second was to design a mechanical and sensor system capable of moving through the lock and taking measurements with the required precision. Lastly, software needed to be developed to emulate the SPP methodology. These objectives culminated in the final aim of an autonomous system capable of defeating a one-pin lock. And here is the end result. The project has reached its goals and the robot is able to defeat this lock. The first step of the project was to design a lock for the robot to interact with. This is of course scaled up from a regular commercial lock and can receive up to 3 sets of pins. This lock is made of a combination of laser-cut acrylic parts, 3D printed ABS parts, and contains steel springs and pins. The lock was designed in SolidWorks, and after 5 design iterations, this is the final result. The CAD files utilize an external file for variables. This allows various lock parameters to be changed on the fly. Parameters such as tolerances and lengths are fully customizable, and even the number and spacing of pins is completely variable. Even when pushed to the extreme, the design is still quickly updated. Take this monstrosity for example. Of course, the lock is capable of being picked. First, a tension wrench is inserted. Light tension is applied and a pick is inserted. The lock is then probed to see where the pins are placed. Then heavier tension is applied, and as the pins begin to bind, they are raised to the shear line, accompanied by some audible feedback. And it's picked. The robot was also designed in SolidWorks and is comprised of several assemblies, mainly the pick assembly and tension assemblies, as well as the X and Y axis systems that move the pick assembly. The pick assembly contains the pick, load cell, and load cell amplifier. The pick is hinged and rests on the load cell, enabling it to transfer the force from the end of the pick to the sensor, and also allowing the pick to lift off the load cell, which is useful for detecting some lock parameters. The X-axis assembly controls horizontal movement. It is driven by a stepper motor and lead screw. The nut housing that holds the Y-axis and pick assemblies runs along the lead screw and is supported by acrylic rails. The X-axis is capable of a wide range of movement, mainly to accommodate the longer pick required for locks with a large number of pins. The Y-axis assembly controls the vertical movement of the pick assembly and rests directly on top of the X-axis assembly. It is driven by another stepper motor, this time with a much smaller pitched lead screw, for an increase in precision. The assembly is capable of positioning the pick anywhere vertically within the lock. The tension assembly controls the tension on the lock. It is built around a 70mm internal diameter bearing with a custom 3D printed gear. It is belt driven by a timing belt from a DC motor, and the assembly boasts both top of the keyway and bottom of the keyway tensioning. Once all the systems were designed, they were fabricated using 3D printing and laser cutting. The assembly process was completed over several days and took approximately 4 hours. After it was assembled, wiring took another 4 hours, and a cable chain was used for neat cable management. The software system was implemented on an Arduino. The system controls all the motion and sensors and is capable of serial communications with a PC. Firstly, the robot zeroes its axes, as the stepper motors have no absolute positioning. It also tears the load cell. It then begins heading towards the lock opening. When it arrives, it will apply tension and begin to raise the pick. Finally, when the load on the load cell peaks, the lock is successfully picked. And the robot returns to its home position. The robot would be improved by the introduction of more metal components. The tension wrenches have a tendency to snap, and the pick has more flex than is ideal. The support rail on the Y-axis seemed ideal when first constructed, but wore as time went on. The acrylic rails for the X-axis also loosened over time. As far as new features are concerned, The program could be run faster if an external controller was used to control the stepper motor pulses. Additional degrees of freedom would allow the robot to pick a wider variety of locks, including paracentric keyways. 2D load sensing would increase the amount of data available and would complement any additional degrees of freedom. I hope you enjoyed my presentation. Thanks for watching.